My name is Jijun Miao. I'm from SimTech, but I always remember I'm a research advisor for our RSJIP, and this is a more honor because I know exactly RSJIP is our resource for all the technology, and also our company got a lot of support for students or after graduating joining our company. We can continually develop all the software from developed and the idea is from utility. So SimTech is our mission is to commercialize our RSJIP's research and to connect to the industry. So our goal is to try to make all our research is really applicable to the industry. So so this is my job as a research advisor. Dr. Kemi Stefanori asked me to give this talk, in general talk about the workflow from geology then to reservoir simulation. My background is geology, so technically I'm a geologist. And we started from around 10 years ago. Now it's 9 years, 9 years ago. We started to talk about simulation. I'm a geologist, so I'm trying to honor all our geological features in our random simulation. But unfortunately, a lot of challenges and limitations we are facing too. So today I'm talking about some of our observation and some of my personal ideas, and also something I'm looking for in the future. We can handle it, or we can make it really resolve some challenges from industry. First of all, is so this is about integrated geological engineering workflow. So here we got all the geology model, and including those straw heterogeneity, depositional, and structure like faults and fractures there. And we honor those grids and we developed ports so that we can import any models like your reservoir model, your geomechanical model from petrol, from open flow, from Joule suite, and into our system. We have those ports. So we try to take advantage of all the geologists and geomechanists of petrophysics, their knowledge, their idea into our system. We call it ZFrac. ZFrac can honor this heterogeneity of the geology or geomechanic. Then we do hydraulic fracture simulations. And after that, our core technology is EDFM. EDFM is embedded shredder fracture model. This is the original from Kemi Stefanori's lead. We developed this software, and then jointly we patented it. And now we commercialize. We are the first in the world to commercialize the EDFM to handle real industry problems. With the EDFM, we can move all our hydraulic fracture and natural fracture explicitly into your reservoir simulator. Of course, we support any third-party software like Eclipse. It's Eclipse or CMG, Navigator, Echelon. We are very friendly to them. Of course, we have our own. You are seeing this is also from UTCOM. And this is a whole workflow from geology modeling to hydraulic fracture simulation, then to reservoir simulation. This we call the geology to engineering workflow. And at the same time, we know this is quite tedious and quite hard work to do it very easily. So we embedded AI. We implement the AI to make it smarter, faster, and easier. So later on, I will talk about something the limitation and some problem we're facing. First of all is from some observation, we found to do simulation accurately, we have some problem. So this is the case for first hydraulic fracture testing site in China. Well, we are very lucky to join that at first beginning. Dr. Kemi Stefanori joined the designing and helped them to build all the framework. And here's just one thing. Dr. Yu mentioned give a talk about this project in in HFTC this year, and in June in RTech, we got an invitation to give a special talk to talk about this project, how we do test all the design it and test it, then in the next phase, how it looks like. This is some observations, very interesting. It's also happened in United States in Permian Basin. We core, this project basically we do these two hydraulic fractures, and then they physically drill two wells. One is cross like this, one is parallel to this fracture, so that we can core all the hydraulic fracture reservoir. Then we can check. This is core from those observation wells, and here you can see that actually fracture is not single fracture. It's we call it swarm, or we call it cluster. So this is actually the hydraulic fracture growth is very complex. Such like this is the bedding layer, a hydraulic fracture is across it. So it's a lot of things that happening. Especially here we have a lot of faults, natural fracture root clusters. So it's all combined together. Hydraulic fracture simulation is not going to simulate everything. It's too complex. Mechanically, you cannot do that. So this is what we did. We gather all the information in our ZFrac software. You can see we honored the microseismic. We got all the hydraulic fracture. So we try to simulate the cluster or swarm pictures, but it's not easy to realize, especially when you try to simulate the paths. So we simplified it, use a planner to do that. So we can observe those well interference. So we match with those fracture we observe. Of course, there's like 300 or 600 fractures we identified with the IFM and with the actual core, and also with those propanes. We calculated a lot of method that will be discussed in the June presentation during the RTech. So this is I'm trying to do the hydraulic fracture simulation or reservoir simulation. We try to be as accuracy as possible. So people always ask, how your software accuracy? Is it that accuracy than other software? That, to be honest, it's a fake. I think it's a fake theory or something. So all simulation actually, I think it's a simplified proxy for subsurface features, and we try to use a proxy. All our simulation is to try to simplify from geology modeling. While we are doing the interpretation for the seismic, actually it's a simplification method. So we just try to find a simple proxy to represent the actual subsurface body, like those fractures. It's a swarm, but we just use a single planar to represent, of course, include some natural fractures as well. And the reason is the GR model is inaccurate as well. For example, right now, majorly in the United States, people do hydraulic fracture simulation using logging data. So logging data, the vertically, it's like about 1 meter accuracy or even more accurate than that. But beyond the wellbore, it's nothing. We just populate from the, that means actually your horizontally, your model is unique. It's all no heterogeneity considered. So how you can do 3D accurate simulation? It's impossible. And we honor some situation like we use this words. So this is a truly 3D model we did for real kids. This is very big. It's around like thousands, 1,000 kilometer squares. And even with the seismic grades, the seismic units is 20 meter by 20 meters horizontally. So this is a truly 3D seismic model, and vertically with the seismic accuracy is less than 10 meter, but still it's very rough one. And the model grade is like 1 billion, more than 1 billion. So you can see if you look into deeply. So this is 20 meter by 20 meters grids. You want to use that model to do accurate 3D simulation. I think it's impossible. So some software, they said that they can do 3D actual simulation. I think honestly to say it's waste of your computational efficiency. So of course, some features they don't consider about the natural fracture and everything. I'm talking about the actual subsurface is really, really complex. This is some in Middle East, they use Thornberg's technology to detect all the fractures, bedding layer or natural fracture. It's observed, actually matters. But in the industry, we use a planner. We just ignore. We pretend there's no natural fracture. There's no faults. But actually it does. Because I'm a geologist, I know that every day. Okay, and so we try to simplify this as planner. Okay, that's okay. That's the same method we are using, but we try to honor those fractures and features as much as possible. And in the reservoir simulation, yeah, we make it even simpler. We use dual porosity, dual probability model. We just merge those fractures into one grid. You can now identify any fracture, single fracture itself. So it's more all blur, like you are using a blur lens to watch your object. It's not going to find it. So what we did is actually we try to honor this. That's why we developed this integrate from geology to geomechanics. We try to simplify, narrow down the uncertainty through introduce the major dominant features like the faults, the fractures, the heterogeneity, the change. Although the grid is very coarse, but still there is some statistic features you can capture. That's why I said, okay, we don't always try to get an accurate simulation. What we need to do is the trend, and we try to find a simplified proxy to simulate the actual body-like fractures. That's what we can do, and it's a smart way. What we need is just functionally they are same. The next one is talking about calibration. We did that for a reason. It's not just okay, I can give you anyone. For example, some software they can do okay. They use a lot of monitor data to try to match it. Between there, you use like just a simple model, how you can simulate the heterogeneity or the phenomena. It's just playing some game. We know that. It's just randomness. You add some randomness, look, it's nice. But we waste so much time to try to do that simple proxy. So we try to make another way, run another way. So anyway, we will use the calibration. So you will try, our method is we don't try to use expensive 3D simulation to try to simulate your process. Okay, we can generate like 1 million cases. 1 million cases, and we will use the calibration to pick out the best matched function one. So this is our method. That's why we value the GPU, we value the parallel computation, we value fast generative simulation. For example, this will have hundreds of more than 100 stages. We can simulate it less than 10 minutes. And we can, after simulation, each stage, we can, in 20 minutes, we can run the pressure history matching. We try to geomechanically to calibrate your model. And why we are confident about that? Because our pressure, behavior, response, our simulation can match it, like 80% or 70%. That's it, pretty enough. So we can get the valid, that means hydraulic fracture generate SRV body. And this is Juicy later on, we'll talk about how we do that with the EDFM ZFrag AI. We can use a smarter method. We can run like just 4 or 5 rounds, and each one we can run 40 cases. When we can quickly get a mesh cases, then we can, okay, this is more confident. This is more reasonable. So I'm not going to talk about the details. Then the same with the production. We use this AI. Now it's a neural network. I don't know what's the detail, but it's really useful. We can run, we honor those base case, and we play with this uncertain parameter like a fracture, half-length fracture height and conductivity, and also matrix information. Then we run it like 7 rounds. You can get your matched cases. So this is some benefits you can get, and of course, that's Chuxi mentioned. We can match with multiple cases. We got multiple match cases. That means your answer is not unique. You have multiple possibility. That's why our parameter is a range. Those decision makers in the United States they like it. They said, okay, it's not a stationary results. Then they kind of like P50 is more representative about this is more like a subsurface uncertainty. You never know exactly what's the answer, but with this range, it's almost cover all the possible parameters, so that we can use those information to do optimization. So that's why with the calibrated model, now we are more confident to do the forecasting. This is the forecasting like years we can get the drainage volume, which is correlated with the recovery rate. And so this is basically what we do. Of course, there's a lot of challenges, especially now with the unconventional now production data, like 10 years is very easily, or 80 years. So there's a lot of activity. They use the foam pipe to increase the value, but this is not a simulator cannot do that. So while you're doing this simulation, you need to work with the field engineers. They knew what happened. So if you are just in-house office engineer, they try to match it. Anyway, they try to make some fake things to match it, but it's nonsense. You are not wasting your time. So we need to smartly analyze your data and then to try to do smarter simulation or analysis. And also, we need a lot of simulation. It's not 10 or 20. We need hundreds of simulation. That's why you need your computation capability. That's why GPU now is a good choice. With GPU, with multiple cases, we are talking about smart learning. Something is the future. Of course, Chuxi just mentioned about this degradation. So we observed from all, it's from HFTS, the results. Hydraulic fracture is shrinking, no matter production or not. Even you just shut down the wells, but still they are shrinking. So that's why all the simulator you cannot change. This is a traditional method, and you cannot match it. In Bakken, we realized the first time this is could be dynamically matched. Now it's more reasonable simulation. So that's a lot of challenges and questions raised up during our actual job. So our people is working with field engineer side by side, even stay in the field with them and try to understand what's happening. Actually, a lot of data is fake. You need to have the wisdom to pick it out and get rid of it, then try to find the trend. And of course, the right solution. This is a very powerful solution. This is newly developed thing. So with this simplification, I think that simplification is a good word. You can make expensive and not a feasible thing. Now we can make it really working. Next is our team is trying to implement those AI or those machine learning into our workflow. We call it vertical application. So we did some testing. First of all, our simulator is actually as powerful as other simulator. But why we are now very unique? Because right now we can run it in real time. This is the TFOC. We developed to work with CNPC together, and it's actually in the field. So every stage, while they are doing hydraulic pumping in the field, in the center, they will run simulation at the same time, simultaneously. So with this, and those engineer or those decision maker, they can even vividly, they can look into what is happening is possible. So this is natural fracture deactivated. There is a screening problem potential. So now we just merge with the first time we merge with the simulation in real time with actually the pumping job in the field. So this is already Tremendous center. So this is the right. This is I sneak in and I let people to shoot it. This is the model. this is pumping. So this is our simulator. So that's how we integrate with the hardware and the actual job in the field. So I'm there in person. So these are our engineers working them team by team. And actually you can see hydraulic fracture. This is all electric part and all pumping. Then simulator. So our engineers is working them side by side. Oh, by the way, the YPF have a really cool center. It's called RTICO, OCO. Yeah. So we are there with Kevin Secondary. They are very proud, but they don't have this real-time simulator. Okay. Yeah. I think the next stage UT can help them to have a real-time simulator so that a decision maker can see, okay, what's possibly happening down there. Is that because the hydraulic fracture, if there is a other way to improve the simulation or optimization. I mean, so this is how continually with those AI, EDF and AI simulation, we can run a prediction more confidently. And with that, this is right now we work with a company. I think I can mention the name, but yeah, maybe for caution. So right now we can run like optimization on our simulator as much as possible. But we are thinking about 1,000 cases, or maybe 2,000. They think it's not enough, maybe 10,000 cases. So we run all the cases here. We get ready the inputs. They run simulation, physical simulation there. Then this is our inputs for AI. So with that, then later on the AI will generate a digital twin. We already tested. We realize it's working. So later on, that means later on you don't need to run this simulation physically. You just run the proxy, or we call digital twin. And this digital twin will be involved with more data, more simulation. And every 6 months or every 2 months or every 2 weeks, we can run that again. This is good news for those computer guys. They said, okay, we got a lot of computational demands. And then first of all, we can use that to do optimization. It's just the clients are very happy because in the office, they don't need to run a physical those simulation, computer simulation. They are just running on a black box. You just go, okay, I want to change the well space like this. So what's the result? We will see that. So how well interfaces like that, we will show that. So this is our goal to make digital twin actually work for real time support the field. So even the field engineer, they just let's play it like play game. We can do that immediately got result. They don't need to run simulator. They don't need those knowledge. Everything will be the same. Okay, now we are trying to focus on the resonance simulation part. Later on, we will move upper to hydraulic fracture and move to the geology or geomechanics. We call it dictionary, geology and engineering dictionary, so that you get like a library. You can check about the results. So later on, you can use that for EUR, EGR, or you can run on this model. So all the features we try to include in that. So let's come back to the new workflow. I think this workflow now from geology to engineering. Later on, we will go to digital twin with machine learning's help and this GPU. Everything is possible. So with that, I think yeah, you are right. All simulation is wrong, but our goal is not to find the accurate, the what's exactly there. We just will find a proxy so that we can quickly to do some simulation to get rid of the risk, potential risk, or narrow down the uncertainty. And now with those AI help, we can do the actually real time and also digital twin. It's reliable. And this is some our achievement with RSJIP, and this is from industry with academic collaboration. I think a lot of companies, they are very interested in our business model and which can value our research, our scientists' value and contribution, achievement. Yeah, that's all. And I'm open to any questions. Thank you. I think it's a Friday, so I'm skipping the questions. Let's go to the next.
Question.
Okay. Okay, welcome.
So you mentioned EOR and EGR.
Mhm.
So one of the challenges I see with the AI and physics informed AI, you're not going to have enough physical data. So then basically you have to generate them with your simulator, right?
Yeah.
So that is a challenge.
Yeah, you are. This is a thank you for this question because this is a value here. For previously we talked about digital mining, data mining or something. So we got data, but for services with the people we can record all the enough samples. But for subsurface, just the whole several holes, it's not enough data for you to learn. So here is a simulation, beauty simulation we can run. This is what I'm talking about. We can run through simulation to run all kinds of possible scenarios and the different well space and the different EOR or EGR the process. You can do simulation. That all will be inputs for the machine learning. So I can generate the digital twin. The digital twin will learn all the physical and all the mechanical behind the scenario, then make it easier. So I think that's later on help people to, although there are no data, but with simulator, we can generate as much as possible data. But you need the speed enough, fast enough. That's why GPU and parallel computation is helping.
Thank you.
Okay, thank you. I'm done with this. Thank you.